in here as goes out here. The number of molecules that come in from here has to be the same as the number of molecules that go out here. Or better yet, the volume of fluid in a small amount of time that passes into this little region here had better be the same volume of fluid that passes out of it. Otherwise, something has to get squished. Otherwise, something has to get compressed, or what's the opposite of compressed? Decompressed. Right. So I can immediately write down the condition for an incompressible fluid. We can think of it two ways. One is to stay in the fluid at some fixed little element there and require that the same amount comes in from the left as goes out from the right. That's one statement of it. Or we could stick with a body, a piece of the fluid, and follow the piece of the fluid, and then to say it's incompressible is to say that the volume of that little piece doesn't change. Okay. To say it's incompressible if we follow the fluid, two ways to think. Follow the fluid, the volume of that piece doesn't change, and the volume change, then it would be either expanding or contracting or compressing. And the other way to think about it is to stay fixed in the space, not move with the fluid, watch the fluid move past you, and say as much must come in here as goes out here. Both of those, they're equivalent statements, and to summarize them, the fluid is incompressible. But what is the condition for incompressibility? Except the velocity has to be uniform right across this line. Or another way to write it is that the derivative of the velocity vector, velocity vector, with respect to x, this is x, must be 0. What happens if the v dx, if the velocity vector, if the v dx is positive? Let's just think about that for a moment. If the v dx is positive, that will mean that as you go to the right, the velocities are getting bigger and bigger. I would say that's decompressing, the fluid is stretching out. So if the v dx is positive, it sounds like it's the opposite of compression. And if the v dx is negative, that means that the velocity over here is large, smaller, 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 and maybe even turning negative, going the other way, if the v dx is negative. It's clear that that's a compressional kind of situation. The v dx being 0 is the incompressible fluid. Alright, now we're going to need the concept of an incompressible fluid for higher dimensions. One dimension will not be enough for us. So supposing we have a fluid in, well, let's begin with let's begin with 2 dimensions. We have a fluid in 2 dimensions, and either we can follow the fluid, take a little box in the fluid, follow it for a period of time. Its shape might change, I don't know what it does, but if it's incompressible, the volume, or in this case the area of that piece of fluid will stay the same. Or we can stand still and focus on a box here, and the condition of incompressibility is that as much fluid, volume of fluid, flows into this region in a small interval of time as flows out. For example, it might be flowing in over here, and flowing out over here. Well, it might even be flowing in over here, but then it better flow out over here, and so forth. That as much flows in as flows out. Now, I'm not going to work out the mathematics of this, probably many of you know it, but I'll just tell you what the answer is. Supposing we have in 2 dimensions here a flow vector, which is Vx and Vy. These are the components of the flow vector. They depend on where you are, x and y. What is the condition that fluid does not build up in this region? So first of all, let's go back to what we said before for the 1-dimensional case. If the fluid velocity is varying across the x-axis here, that's bad. It means it's either compressing, more fluid is coming in one side and going out the other. So we said that dv by dx got to be 0. But it's pretty clear that dv by dx, let's write partial derivatives, since we're now in multiple dimensions. The partial derivative of the velocity, and in particular the x component of the velocity, this is how the x component of velocity is varying as you change x. So if the x component of velocity is small here and big here, then the fluid is stretching. That's some measure of how much the fluid is stretching in this direction. But all we're interested in is following the volume. If the fluid is stretching in that direction, that's okay, as long as it's compressing in the other direction. If it's stretching itself out in this direction, it can still maintain its volume and still not be compressed if it's being compressed in the other direction. Phase space, phase space, phase space. Yes, absolutely. Absolutely. This is a general statement about a fluid in any number of dimensions, that the condition that it's incompressible is not that the derivative of dx with respect to x is equal to 0, but that the sum of them. The derivative of the y with respect to y plus the derivative of the z with respect to the z is equal to 0. The first term measures how much compression there is along the x-axis. If the x component, incidentally, as far as the x squeezing goes, the y component of velocity doesn't matter. What's important is how much the x component of velocity is changing as you vary x. Now what these stand for is the combined sum of the compression along the x-axis, the y-axis, and the z-axis. Let's get this three coordinates down. Z. And that's the condition that the flow of the fluid is incompressible. Now, this symbol, or this quantity, the derivative of the component of a vector field, the x component of the field with respect to x, plus the derivative of the y component of the field with respect to y, plus and so forth, has a name. Does everybody know what the name of it is? The divergence of the vector field. The divergence is some measure of how the vector field is spreading out at any point. This is the divergence, and the symbol for it. There's a symbol for it which is del dot v. The del stands for the derivatives, the v stands for the vector field, and the dot product, it looks like it's a dot product between a del symbol and a v symbol, but it doesn't matter. This is what it is. This is what it is. The sum of the various components of the velocity field with respect to the same coordinate. That's called the divergence of the flow. It's the spreading out, or the compression. Now, having talked about this flow, and as I said, it's an equivalent question to ask if you stand at a point and require that the total volume of fluid that flows into that region is the same as the amount that flows out. That's equivalent to following fluid and saying that in a chunk of fluid, the volume doesn't change. They're equivalent statements. Okay, let's abandon this whole line of thought for a moment and return to the very first lecture. And remember what we said? We had some kind of system which was characterized where some sort of space of configurations. Put another one over here. It's a it's a die with 7 faces. 1, 2, 3, 4, 5, 6, 7. Yeah. And we drew some arrows to indicate how the system moved. The arrows are in some sense very, very similar to this idea of a flow, phase space. They're telling you where to go next, is what they're doing. We gave some examples of good laws of physics. I'm not going to draw a good law of physics, but what is true of a good law of physics is that at every point what flows in you're at this point, you know where you'll be next, and you also know where you were just before, unambiguously. Well, that's somehow saying something that sounds a little bit related. If I take a little box around here, as much flows in as flows out. One arrow in, one arrow out. We could even do something, let's go to the six-sided case for a moment. We have laws of physics, for example, which look like this. That was a particularly simple one. We could take a couple of points and we could follow them. 2 points to 2 points, they move around on the cycle here. 2 points to 2 points to 2 points. The number of points, if I start with 2 points and follow them, they stay 2 points. They stay 2 points. So in some sense, if we thought of the number of points as a kind of volume, the volume is conserved if we follow the system around here, or we could say it the other way. If we focus on a particular node here, the number of arrows in is the same as the number of arrows out. By contrast with some bad laws, here's a bad law. No matter where you start, you go to the central point. No matter where you start, you go to the central point. That's an irreversible law. You may know where to go next, wherever you start, but if you find yourself over here, you don't know where you came from. Okay? Well, if I draw a box around here, I notice that it's not true that as many arrows come in as go out. More arrows come in than go out. That's the nature of an irreversible law. So it almost sounds like in this discrete, simple-minded 6-state system or 10-state system, or 7, whatever it happens to be, that the law of reversibility sounds almost like saying that the fluid is incompressible. And in fact, if the fluid is incompressible, that sort of means that, it means something like this. It means a continuous version of the same idea, as much in as out. So the question then is the flow of the fluid in phase space dictated by Hamilton's equations? Is it such that it's incompressible? Another way of saying it is if you start with a volume of phase space, a little volume of phase space, and follow it in time, does it occupy the same volume afterwards? Or does it have an effect of getting squished up so that things which were clearly distinguishable and different from each other get squished into a smaller region where they can be less distinguished? That's the question. So I'm going to show you now with Liouville's theorem. Liouville's theorem is a theorem that says that the flow in phase space is incompressible. It's the closest thing that we have, closest analog that we have to this idea that, this idea that as many points come in as go out of a given point here.
Just to clarify, the V's are P dot and Q dot.
These are P dots and Q dots. Right. So we line up all the P dots and Q dots. Let's think of our velocity vector. Well, I'll tell you what, let's start with just the case with 1 P and 1 Q. And then generalize it to any number of P's and Q's. So we have 1 P and 1 Q. Q, P. And what is the velocity vector at every point? The velocity vector, let's call it V sub P and V sub Q. These are the components of the velocity vector. And by definition, Vp is P dot and Vq is Q dot. Okay. So, this phase space here is filled up with a velocity flow where the components are P dot and Q dot. Now let's calculate the divergence of the flow. The divergence of the flow is the derivative of Vp with respect to P plus the derivative of Vq with respect to Q. If you here, this is minus d by dt of dh by dq. And what's this one over here? This is plus d by dq of dh by dp. I think we must have mentioned at some point about partial derivatives, that the process of partial derivatives is independent of the order of the differentiation. I think I hope we mentioned that because we didn't, we'll mention it now. If you have the second derivative of a function with respect to two independent variables, it doesn't matter which order you differentiate. That's a little theorem. It's a very simple theorem. I could show you on the blackboard why it's true, but I think did we do this sometime? Never? Oh yeah. This clear? Alright, get up and prove it. Let's prove it. Let's prove it. Let's label 4 points here. A, B, C, D. And we have a function of the 4 points. Right. And this direction is P, and this direction is Q. Alright. What's the derivative of the function with respect to Q down here? Well, let's call it VC minus VD, right? We should put a little epsilon in the denominator, but basically the derivative of some function, and whatever function it happens to be, function. The derivative of a function with respect to Q is just the derivative as you move along the Q axis. Now, what's the derivative with respect to Q up here? That's f of B minus f of A. So now, let's consider the derivative with respect to P. That's differences going vertically of the derivative of f with respect to Q. D by dp. That's just a difference of this and this, right? It's a difference of differences, but the difference, this one tells you to move vertically, this one tells you to move horizontally. So the difference between this expression and that expression